Okay, so we've been talking about solutions of systems of equations, and we talked about a graphing method. And then in the last example, we graphed a system. We graphed both equations, and then they crossed in one place, and then that point of intersection was a solution to that system. But we want to ask ourselves, would it be possible to have an infinite number of solutions? Would it be possible for two lines to intersect in more than one place? Well, we would think maybe no, because we're thinking of maybe two different lines that are trying to cross in two or three places. But what if they cross in infinitely many places? What if I give you this system? Y is equal to x plus 4 and negative 2x plus 2y is equal to 8. Okay, if we were to graph this system, let's take this first equation. Let's find x and y intercepts, and then we'll draw the graph. So to find the x-intercept, we have to make y 0. So 2 times 0 is 0, so this term is eliminated. We have negative 2x is equal to 8. So if we make our xy chart, we're going to make y 0, and we want to find x. In this second equation, we're working on the second equation, not the first one yet. So if we look at the second equation and we plug 0 in for y, we get negative 2x plus 2 times 0, which is 0, is equal to 8. So if I divide by negative 2, I'm sorry, on both sides, I get x is equal to negative 4. So that would be 1 point. Okay, to find another, let's say find our x-intercept. I'm sorry, that was our x-intercept. Let's find our y-intercept, okay? To find our y-intercept, we want to make x equal to 0. So let's take the second equation, let's plug in 0 for x. So negative 2 times 0 is going to be 0, and so we just have, so we plug a 0 in for x, and we're just going to have 2y, that doesn't look good, 2y is equal to 8, and if I divide by 2 on both sides, then I get y is equal to 4. Okay, all I'm doing is I'm taking 0 and I'm plugging it in the second equation for x. So negative 2 times 0 is going to be 0, plus 2y is 8. So really I just have 2y is equal to 8. And then if I solve that, I get y is equal to 4. So that's what I get. So this is my chart that I have. Okay, so if I plug these points in, remember these are just ordered pairs, so like negative 4, 0. So like negative 4, 0, that's going to be my x-intercept. My y-intercept is going to be 0, 4. Okay, so my line is probably going to look something like this. Okay, something like this. Okay, so but now let's graph the second equation. Okay, if I graph this equation, it's already in y equals mx plus b form, so it's kind of ready to go. If our y-intercept is going to be 4, and then our slope is 1, so we're going to rise 1, run 1, rise 1, run 1. So in fact, it looks like it is the same line. So really, when I gave you this system of two equations, really it wasn't two equations, it was one equation. And I just listed it twice. So what that means is that these two equations, although they look different, are actually the same. If I took this equation 2 and I tried to solve for y, if I moved x to the other side, it would become 2y is equal to 2x plus 8. And then if I divided both sides by 2, then this would become y is equal to x plus 4. And that was my first equation. So really when I gave you this system, I didn't give you two equations. I gave you one equation twice. So every single point is going to be a solution because every single point lies on both lines. Remember the rule. The rule is wherever they intersect is a solution. Here they intersect everywhere along this line. So then that means that every single point on the line is a solution. So since they touch in infinitely many places, then there are infinitely many solutions. And so that's what a system would look like if it had infinitely many solutions. Now note, a system of this type is called dependent. Okay, it's a dependent system. Okay, the reason it's dependent is because since there are infinitely many solutions, to find a solution you would have to choose a value for one of the variables first. So you can only find what y is depending on what x is, or vice versa. So one of the variables would always depend on one of the others. Okay, so let's talk about no solutions. What would the graphs look like if the system had no solutions? If the system had no solutions, that means that the lines cannot touch in any places. So the only way that can happen is if you have two lines that are parallel. Now, maybe these aren't exactly parallel, but they're supposed to be. Okay, so here, if you have two lines that are parallel, they're never going to touch. They're going to touch in no places. And since they never intersect, then there will be no solutions. Okay, and so also note that a system of this type is called inconsistent. Remember, we called it consistent if it had exactly one solution. We call it inconsistent if it has no solutions, and we call it dependent if it has infinitely many solutions. And those are the only type of scenarios you can have. Either infinitely many solutions, one solution, or no solutions. So it's either consistent, inconsistent, or dependent. Okay, now let's talk about a method to solve a system by substitution. Okay, here's the procedure. The first step is going to be to solve one of the equations for a variable. So take one of the equations and solve for x or y. You can choose whichever is easier. Okay, then what we're going to do is we're going to substitute what we find in step 1 into the other equation for that variable. Okay, so I'll show you what we mean in a moment. Then we're going to solve the equation that we get from step 2. We're going to substitute the value for the variable that we found in step 3 into one of the original equations and solve for the other variable. Then we're going to check to see if the ordered pair is actually a solution. So let's look at an example. Okay, if I want to solve this example, it says to solve the following systems of equations by substitution. So remember, step 1, it said solve one of the equations for a variable, either x or y. Okay, so we can choose here. Let's solve the top equation for y. Okay, so sometimes it's helpful if we kind of list these equations. If this is like our equation 1 and this is our equation 2, let's take equation 1 and let's solve for y. So we have 2x plus y is 4, but I want to solve for y, so I'm going to subtract 2x from both sides. Then I'm going to get y is equal to negative 2x plus 4. Okay, so that's what y is. Y is equal to negative 2x plus 4. I need to now take that value, and according to the second step, it says I need to take that and plug it into the second equation. I need to plug it into the other equation. So remember, we got y is equal to negative 2x plus 4. Step 2, it says substitute the expression that we find in step 1 into the other equation. So remember, we found y was equal to negative 2x plus 4. So since we found that y was equal to negative 2x plus 4, we found that from equation 1, we need to take this knowledge and plug it into this equation. Okay, our goal is to have only one variable because we've talked the whole course about how to solve equations that have one variable. Okay, and so since this equation, equation 2, since equation 2 says that 4x plus 3y is 10, but we found from equation 1 that another way to say y is to say negative 2x plus 4. So that means here, instead of saying y, I can say negative 2x plus 4. And then the good thing about that is I'll have only one variable. So instead of writing y, I'm going to write negative 2x plus 4. The reason we call it the substitution method is because of this step. We're taking this information and we're substituting it in for y. So all I'm doing is I'm rewriting equation 2, but instead of writing y, I'm writing negative 2x plus 4. So now I need to do step 3, which said to solve the equation from step 2. So that means I need to solve this equation. So to solve this equation, I need to distribute. So I'm going to get 4x. And then 3 times negative 2x is going to be negative 6x. 3 times 4 is 12. Remember, this is a minus. That's going to equal 10. So now to solve this, I need to combine like terms. I'm going to get negative 2x. Okay, I'm going to have to move this to the other side, and that's going to become negative 2. And then when I divide, I'm going to get x is equal to 1. Okay, so that is my x value. Now, I'm almost done with my solution. Okay, I found what x is. Okay, x is going to be 1. So, since we know that, step 4 says we need to substitute the value for the variable that you found in step 3 into either one of the original equations and solve for the variable. Okay, so remember, we found that x was equal to 1. So now I need to take that information. Step 4 says I need to plug 1 into x for either one of these equations. I can choose either one and it will work. Okay, so choose whichever one. I don't know, let's say equation 1. So remember, this is our equation 1, this was our equation 2. We found that x was equal to 1. So now let's take that and let's plug that into equation 1. So if we plug that into equation 1, then I'm going to get 2 times 1 is 2, plus y is equal to 4, and if I move this to the other side, then I'm going to get y is equal to 2. So that means that the solution that I have, supposedly, at this point, is 1, 2. Okay, that's my ordered pair, that's my solution. But remember, in example 1 gave us the solution, and we had to confirm that it was a solution. And that's what step 5 asks us to do. We have to check to see if it is actually a solution to the system. So let's take 1, 2, and let's plug it in and see if that really works. So if we take our value, sorry, the pen got away from me. I said that the solution should be 1, 2. That's what we're thinking at this point, so let's check it. If we plug it into the first equation, we're going to have 2 times 1 plus 2 is equal to 4. Is that true? 2 plus 2 is going to be 4. So that's going to work. Equation 1 works. Let's plug it into the second equation. 4 times 1 plus 3 times 2 is that 10. Well, 4 times 1 is going to be 4. 3 times 2 is going to be 6. And that does indeed equal 10. So that means that this is indeed our solution. It's kind of a big box, but that should be our solution to the system. Okay, now let's look at another example.